So, this is the final topic of relation. This is just a special type of relation. Relations having certain properties is called partial orders, and because it has many applications in scheduling and optimization and graph algorithms and stuff. So, I want you to be familiar with it. There is a lot you can talk about it and a lot you can do about partial orders in PO sets, okay, partially ordered sets. Okay. So, please pay attention to this thing, okay. Suppose these are the courses, the CS required courses or core courses that every CS students is going to take, right, or is required to take. Of course, between courses there are dependencies, there are prerequisite and co-requisites, and then there are, I don't know, maybe post-requisite at some places. So, there is some example of this. CS100 must be taken from before all these courses, right. So, it is like a prerequisite of all these courses, must precede all these courses. CS202 and 210 must be taken before CS310, right. It is made up, most probably it makes sense, but even if it does not, then it is not a thing. CS341 and 381 can be taken in parallel. Right. So, can be, you may or may not take it in parallel, but there is no required dependency between these two things, right. These systems, such precedence or dependency constraints are modeled by what is called a partial order, right. So, apparently, there is not much there, but this relates, you see a couple of courses, pairs of courses. So, a binary relation is what relates things in terms of kind of by ordered pairs. These are those kind of ordered pairs that we can do this thing, okay. So, a relation on a set is a subset of, a relation on a set A is a subset of A cross A, right. So, that is a recollection for the definition. Now, if the relation is these three properties, then we call it partial order. Okay. Recall that when we had a relation on a set A or a set X, it was called an equivalence relation if the relation is reflexive, meaning every element of X is related to itself, and the relation was symmetric, meaning if A is related to B, then B is also related to A, and the relation is transitive. If A is related to B and B is related to C, then A should be related to C. That was an equivalence relation, right. So, the difference between an equivalence relation and a partial order is this thing. A relation is called a relation on a set X is called a partial order if it is reflexive, it is antisymmetric, and it is transitive. Remember, we talked about symmetric and antisymmetric are not the negation of each other, right. Not symmetric can be something else. A relation can be symmetric and antisymmetric simultaneously. A relation can be neither of them or something, but this is, these three conditions, properties have to be there in a relation, so it will be called a partial order. Okay. This is some it gives an order to the sets that may not have a natural order. So, we will talk later about well ordering, total order and well ordering. This is when there is no order. So, like these courses, it is just no order, it is a set of courses, right. It is an unordered set of courses, but if we want to impose on top of it some order, some partial order, we will see why is it called partial order. Then that is why then we will define a relation between them, and that will model everything, right. So, note the notations. A precedes B. This notation, A precedes B, is when A, B are related by this order, by this partial order, a relation with these three properties, then this is the notation for this, right. It's denoted as A precedes B. Okay. This is A precedes B, like strictly precedes B for unequal thing, right. So, if A is different than B, then we write sometime like this, but generally we write like this as usual thing when we say A is less than or equal to B from the context or from something, it is generally sometimes it is clear that we mean it is not equal, it is just strictly less than, right. So, do not confuse this thing. A precedes B, that is how it is pronounced, and in LaTeX you will write slash precede, A slash precede B. It does not mean less than or equal to, okay, it precedes, it is a different thing, okay. It denotes a partial order. So, one more term and then we are done with the partial order and the related terminology. The set, the ground set, the set on which a relation is defined together with the relation, the partial order, it's called a partially ordered set. It's a set. Now, this relation makes it partially ordered, right? It's called a poset, a partially ordered set. So, if you hear this word sometime, don't be scared of this, okay? Too such big words, nothing there. So, earlier we talked about it, the equality relation on the set of integers was an equivalence relation, right? Because it's reflexive, every number is equal to itself, it's symmetric. If a number is equal to B, A is equal to B, then B must be equal to A. N is transitive. If A is equal to B, then N B is equal to C, then A should be equal to C. That was a relation which was an equivalence relation. The set greater than or equal to A, is this equivalence relation? Greater than or equal to on the set of integers. The ground set is set of integers, the domain is set of integer, and I define two things to be related if A is to be related to B if A is greater than B. Is this an equivalence relation? So, let us see, is it reflexive? A greater than or equal to B, is it reflexive? Right, because every A is greater than or equal to A, so it is for every A, this is true. Is it symmetric? Right, because if A is greater than or equal to B, then B is greater than or equal to A only if A is equal to B, right. So, only for equal thing this bidirectionality is allowed, and it is transitive because if A is greater than B, greater than or equal to B, and B is greater than or equal to C, then A should be greater than or equal to C. But so, it is not an equivalence relation, but it is a partial order, right, it is a partial order. So, this is the partial order, you can give it like this. So, this is all of these things related, some of those elements that are related by this relation greater than or equal to relation, these are elements in the, these ordered pairs are in elements of the greater than or equal to relation. Okay. So, we know this is a partial order because greater than or equal to imposes a reflexive relation on the integers, right, because every element is greater than or equal to itself. So, for all A is greater than or equal to A. So, it is a reflexive relation. It is an anti-symmetric relation. If A is greater than or equal to B and B is also greater than or equal to A, then the only possibility for that is that A should be equal to, A should be the same as B. Right, we are talking about the same thing. So, it is an anti-symmetric relation and it is transitive, right. A greater than or equal to B and B greater than or equal to C means A is greater than or equal to C. So, this is a partial ordered, and this thing Z together with this relation greater than or equal to is a poset. Okay, it's a partially ordered set. Okay, nothing fancy, just words, just remember. You don't even need to remember this, the three conditions here, but if you do, it's a good thing, right. And the best way to remember this is to remember also the equivalence relation. Okay. Okay. So, is Z less than or equal to be a poset? Z with together with the relation less than or equal to, is this a poset? Right. So, we need to argue that less than or equal to relation is a reflexive relation on integers. Right. So, is every element, if every element of the set integers, a set of integers less than or equal to itself, right, every A in Z is less than or equal to A, right. So, this is a reflexive relation. Is it anti-symmetric? Well, just like greater than or equal to, if A is less than or equal to B and B is also less than or equal to A, then A must be equal to B, right. And it is also transitive. If A is less than B, less than or equal to B and B is less than or equal to C, then A should be less than or equal to C, right. So, whenever I see these two, I can add the third one, or the third one must be there. So, this is also a poset, right. Okay. The divisibility relation on the set of positive integers. So, we are talking about sets Z plus only, and the divisibility. So, what is the divisibility relation? A is related to B if A divides B. Okay. A is related to B if A divides B. So, does any number divide itself? Any positive integer divide itself? Right. So, it is a reflexive relation. It's a reflexivity is there, right. Now, if A divides B and B also divides A, then should they be, can it happen that a number divides a different number and that different number also divides the previous one? Could it happen? So 2 divides 6, right? Does 6 divide 2? Does 6 divide 2? 6 is a factor of 2? 6 is, sorry? So it's not, right? So whenever x divides y, then y does not divide x unless x is equal to y, right? So 2 divides 2 and 2 divides 2, that's something. So that's the anti-symmetry requirement, okay? And transitivity, if a divides b and b divides c, then does a divide c? So let's say when I say a divides b, what does it mean? That means b can be written as a times some number k, right? Some integer k. That's what it means. B is a is a factor of b, okay? And let's say b divides c, meaning c can be written as b times some integer l, okay? So if a divides b and b divides c, then should a divide c also? All we have to do, we have to say that c can be written as a times something, a times some integer, right? So c can be written as a times some integer. That integer in this case will be k times l, right? Just substitute b instead of b, just substitute write ak. So then I can write c is equal to a times that k times l, right? So k times l is an integer. So c can also be c is also divisible by a. Yes. Yes, this I am defining for positive integers. Okay. No, it may be for all integers also, but we are talking here about positive integers. Okay. Well, that's a very cool, good idea. Suppose instead of z plus it was z, then would it be a partial order? Why not? Sorry? 0 doesn't divide itself. Okay, suppose it was for non-zero integers, positive and negative. Then will it be reflection? So you are right. That's one reason. But now I want to see you to pay attention to. Sorry, please say it again. It's not anti-symmetric. Yes. What did you want to say? You raised hand here, right?
2 divides minus 2 divides 2.
Yes. So negative 2 divides 2 and 2 also divides negative 2. So that here we got a bidirectional relation. 2 is related to negative 2 because it's a divisor, and negative 2 is related to 2 because it's a divisor, while 2 is not equal to negative 2, right? So that's why we just put it that this works for positive integers only. Okay, this is what is commonly used, the subset relation on the universal set of a given set X. So you have some set S, and you consider its power set. That this S is the ground set or the domain or something, the universal set. You consider its power set. Okay, and now two subsets of S are related if a subset is a subset of another subset. Okay, so let's just do this thing. Suppose S is ABC. How many elements are there in the power set of S? Which elements are there in the power set of S? How many subsets? 8, right? 2 to the 8, 2 to the 3. Okay. Now I'm going to draw a relation, make a relation. So let's say one subset. Give me a subset of S. Small subset of S, the set containing A. Is it a subset of the set containing AB? Right? So the set containing A is a subset of the set containing AB. Both of them are subset of S, right? So A and AB are related. Yes? Is this clear? So you know what do we mean by this relation. Now is this a subset, a partial order? Okay. So take any subset of S. Is it a subset of itself? Take any subset of S, it is a subset of itself, right? Because any set is a subset of itself. So we know that, right? So now let's see. If A is a subset of B, you take two subsets of S, One is A, the other is B. If A is a subset of B, then can B be the subset of A? Can B be a subset of A? If A is a subset of B, can B, or in which case is B be a subset of B can be a subset of A? Unless A is equal to B, if A is a subset of B, then B cannot be a subset of A, right? So only in case of equal, this bidirectional relation is available, right? So it's an anti-symmetric relation. And also the transitivity, if A is a subset of B, anything that is in A is also in B. And B is a subset of C, meaning anything that is in B is also in C, right? So that means A is also a subset of C, right? So it's a transitive relation. So the power set of S together with the subset relation is a poset. It's clear? So this is commonly used in a lot of submodular optimization theory. This whole theory of matroid and submodular optimization is actually working in this poset. Okay, typically this is the most commonly used partial order that we work with, and in applications in social network analysis and in many other things. Okay, let me just give you a relation. It's a relation on the set of people. Again, whenever I say set of people, these are just vague words, so just think of people alive or people in the known history or whatever, right? Now x is related to y, xy is in this relation R. If x is older in terms of age, older, if the age of x is greater or equal to or greater than the age of y, is this a partial order? Is the relation clear? X is related to y if x is older than y. Is this a partial order? It's not antisymmetric. It is antisymmetric. If x is older than y, then can y be older than x? It's not reflexive. X is not older than itself, right? No, themselves. X is not older than x, right? The age of x is not greater than the age of x. So it is antisymmetric. It is transitive. If x is older than y and y is older than z, then we can say that x is older than z, right? That is true, but it's not reflexive. So this is not a partial order. Okay, and R, the set of people, comma, this relation, older relation, is not a partial order, not a poset. Okay, so to do a few example, many more example, and nothing there. Okay, nothing there, nothing fancy. You need to understand relation and just see what's given there. Some associated terminology, and then how do we use it, and why is it called partial order? That thing is going to be coming here. Comparability. Two elements are called comparable in a poset. You are given a poset, a set and a relation associated with it, which is a partial order. Okay, so a set and a partial order. We say that x is A is comparable to B if either A is related to B or B is related to B. A. We know they cannot be both ways, right? It's a partial order. So if either A precedes B or B precedes A, then we say they are comparable. Okay. It's comparable. We saw this, when we see the word comparison in algorithms or programming. What does come to? What is comparator operators in C++? Less than, equal to, greater than equal to, and those kind of things, right? And I gave you the first example we saw was greater than equal to. The second example we saw was less than equal to, right? So that's the same comparison. Now see if we can compare stuff or not. So we know what is comparable. So remember I gave you a poset, right, where there was some relations were given that CS100 must be taken before all others, and some of them are can be taken in parallel, and some, right. So CS in that relation, CS100 precedes CS210, right. So these two are comparable, right. We can compare them. So they are related. They are kind of, there is some order set between them, right. if they are incomparable, so CS210 comma CS202 is not in that R. Neither is CS202 comma CS210, right? It's in neither way related. Neither A is related to B or B is related to A. In that sense, in that case, we call it incomparable pair, right? This pair is incomparable, or these two things are not incomparable. Okay, so let's think of this divisibility relation. Poset Z plus is a set of positive integers. Divisibility relation, so if A divides B, then the A is related to B. Are 3 and 9 comparable? Why is 3 and 9 comparable? Because 3 divides 9, that's why 3 9 is in the relation, right? Is 9 and 3 comparable? No. 9 and 3 comparable. Why not? What does it say here? Is either 3 divides B in this terminology, it will mean either 3 divides 9 or 9 divides 3. In both cannot happen, it's like kind of an exclusive OR between them, but forget about that. Either 3 divides 9 or 9 divides 3. So, as 9 and 3 are 9 and 3 comparable? Yes. So, here in this English sentence there is no order. It says in some order 3 and 9 should be there. Is 4 and 6 comparable?
So, what do you mean 3 should be a factor of 9?
No, look at the definition is given comparable. Two elements A and B are called comparable if either 3 divides 9 or 9, if A divides 9, B, or B divides A. This is in either direction. If there is a relation between them in either direction of precedence, whoever precedes, right? So, they are comparable. There is some constraint between them. They are ordered, right? A must precedes B or B must precede C. If they are not ordered, if they are left free, incomparable, then we leave them. Okay, so answer my question. In this poset, is 3 and 6 comparable? Are the pair 3 and 6 comparable? Why? Yeah, okay, good. Is 9 and 6 comparable? Why not?
6 does not divide 9, 9 does not divide 6.
Yeah, is 6 and 9 comparable? 6 and 9. Yeah, Rabbi, let's take with this. Na? We can do many other things, but I just want you to understand comparability. Okay, is 6 and 9 comparable? Why not?
6 does not divide 9,
and 9 does not divide 6. Okay, so that's what is it. Okay, is 5 and 7 comparable?
No.
What is 5 comparable with?
10.
What else is 5 comparable with? 1. Right, 5 is comparable with 1, 5 is comparable with 5, 5 is comparable with 10, 15, 20, 25, right, all of them. Is this clear? Yes? Okay, so we know comparability. Okay, so this is now going to give us the answer. This is now going to give it the next main concept, total order. A total order, totally ordered set or total order, like partial order, hopefully the word partial will be clear there. A poset, a set together with a relation, a partial order relation, is called a total order if every pair is comparable. Okay, if every pair is comparable, then we call it a total order. Okay, total order. In partial order, this like we saw this was a partial order, but we found one pair of at least one pair which is not comparable, right? But if everything is comparable, then we say these are partial order, total order. Okay. Now, if you remember in the first day or the second day, we started this whole thing that much of computer science, much of data science and algorithm design comes down to comparison. Okay. We can compare numbers, right? We can compare positive numbers, we can compare real numbers, we can compare negative numbers with each other, across each other. But the moment things become this thing, two-dimensional numbers, now we can't compare. Now there is statistics, data science or machine learning comes in, right? Find the best student. Now, best student is what? A student is described by too many things, there are too many attributes, there is high dimensional data. How do you find the best student? Well, based on physics grade or based on chemistry grade, or based on the sum of the two, based on the minimum of the two or the maximum of the two. No, it needs a definition. We can't compare. That's word called apples and oranges comparison. That is here exactly that thing. If a thing have total order, if it's total order, then we can compare any pair of elements. But in a partial order, we may not be able to compare, right? So, in this case, which course should we take first between these two, CS210 or CS202? Either of them. It's not, so that's, you see, there is no order defined, it's a partial order only. Between these two, I know exactly which one has to be taken first before there is a dependency constraint between them, right? But these two are, the other two were incomparable. Okay, so we saw this thing, this relation z and less than or equal to, this was a partial order. It's also a total order. You pick any two numbers, we can either a is less than or equal to b or b is less than or equal to a. It's called a dichotomy law, right? It's just, it must be the case. If you take any two numbers, we can't say that either one is a divisor of the other or the other is a divisor of the first one, right? You can't say that either 4 divides 6 or 6 divides 4. But less than or equal to, we can say. So, this less than or equal to partial order, this z together with less than or equal to this set is actually a total ordered set. Okay. So, so if I replace this thing with less than equal to with less than, what is it still a total ordered? Why not? Yeah, so it's not a partial order. So if it's not a partial order, then it cannot be a total order, because the definition says a poset has, if it has this additional property of each pair being comparable, right, then it's called a totally ordered set. So it's not partial order. Suppose there are something called the reason I want to the reason I gave this total order thing, there is something called a strict partial order. Okay. So let me just some books will use this, and sometime in some books the partial order definition is given as a set and a relation which is antisymmetric and transitive, but not reflexive, irreflexive. It doesn't allow things to be reflexive, to be related to themselves, right? In those cases, those are sometimes called strict partial orders. Okay. So, if it was a strict partial order, and then if I define total order also over strict partial order, so this will be then a strict total order. Okay. But anyway, right now in terms of our terminology, so far this is not a total order, right? Less than or equal to is a total order. You pick any two numbers, I can tell you whether A is less than B, right? If you take any two numbers, I can tell you which one is greater and which one is not greater. I can compare them. But if it's less than, then you can't write a code. So think about it. If I don't allow A to be equal to A, then so it's not a partial order, right? Can you see this? Have you ever write comparable? Have you ever implemented or extended? It's called implemented in Java. In C++ also it's called implemented. Comparable. Do you know comparable, Homera? Comparable thing. Have you ever worked on comparable? No. So why? So you guys know objects, structures, right? Two more dimensional, higher dimensional data types, right? You can make structure or object or something. Now suppose I have a student objects, and there is a student name or ID, and then physics score, chemistry score, math score. If I want to sort these students, sort these objects, I have an array of objects, students objects, different. I want to sort them. What can I do? Can I call the C++ or the Java function sort, math.sort, or what is it called? Python, there is a lot of sort stuff. Can I do that? Why not?
So because the standard
Yeah, so the sort function is defined, the comparator is not known. So for that, what we do is typically it's something like this. I don't know the format. I don't do much programming lately, but essentially what you write exactly, you call the sort function, but you say it extends the comparable thing. You write a comparator function. The comparator function takes two objects of whatever type and it returns one if you want to, and it returns 0 the other way around, right? So these kind of things, if you're working with a poset, right, it's not a total ordered set, and you want to sort them, you want to find the median, you want to find whatever data science you want to do, you need to come up with a comparator, right? And the moment you come up with a comparator, it's called extending the comparable, extends comparable or something, implements comparable. That function will convert that partial order into a total order set, and now you can do sorting or other stuff. Okay, one more term, well ordering. This we'll talk more about it in induction. The principle of well ordering. So well ordering is defined as follows: we take a partial set, a poset, a set together with a partial order. It's a relation. And we say that it is a total ordering. In addition to total ordering, there is one more property. You take any non-empty set, there is a minimum. Right? Take any non-empty set, then there should be a minimum. If there is a minimum, then we say the set or the system is well ordered. Otherwise, it isn't well ordered. Okay? So the natural numbers, let me just quickly give you this thing. The natural numbers together with less than or equal to, the n less than or equal to, we know less than or equal to is a poset, right? N less than or equal to is a poset. This is total ordered because you give me any numbers, I can tell you whether one is less than or equal to b or the b is less than or equal to a, right? Any pair is comparable. This is also well ordered. You take any subset, there will be a minimum, right? This isn't true for real number. So let's say, is z less than or equal to a well ordered set? Z less than or equal to, is it total order? Z less than or equal to, we saw this was a partial order. Is it a total order? We saw this in the previous slide that this was actually a total order. You take any two numbers, you can compare them. Either one is less than or equal to b or b, the other is less than or equal to the first one. We know it's a total order. Is it a well ordered? Is it a well ordered set? If I take any subset, will there be the smallest? Any subset of this, will there be a minimum? Yes? No? What if I take all negative integers? Is there a minimum?
Yes.
If you take all negative integers, which one is the minimum? I take all negative integers, which one is the minimum? Minus 1 is the minimum? All negative integers. So what happened to minus 2? Isn't it smaller than negative 1? Negative 7 is smaller than negative 1, right? Which one is the minimum? There's nothing called minus infinity, that's just our creation, right? There's nothing called. You come up with anything that's a minimum, I'll say, okay, subtract 1 from it, that's even smaller than that. And that's an element of this set, yes?
So, but you said that for a particular subset, if you let's say pick out 10 numbers from that particular subset will have some element.
Okay, good thing. So this, look at this word, not for about any non-empty set. You give me any non-empty set, as long as it's non-empty, then you have to be able to come up with the minimum, right? So I gave you an example. N less than or equal to is a poset. It's a total ordered set, but it's well ordered also. Z less than or equal to isn't. Z plus less than or equal to is a poset. Okay. Z minus less than or equal to is not a poset. Z less than or equal to is not a poset, not a well ordered set. Okay. Again, just words, so don't get scared of this and try to use it in your, you should be able to use it in your terminology when you talk about this stuff. So, well, there are too many other things that I want to. So, I recently published a paper on the most ugly thing in the world called cricket. So, the paper does this thing. So, we want to do, so you know Duckworth-Lewis, Duckworth-Lewis turn system, DLS method, you know DLS? No? Okay, good. How many of you know DLS system? Raise your hand, please. Can you note down your names? How many of you are watching that cricket stuff, World Cup? Really? You're not watching it? Come on. Anyway, so there we wanted to do this thing, okay? So this Lewis guy from the Duckworth-Lewis, and they're great statisticians and data scientists. They worked. This is pretty much the only serious data science done in for cricket. So they so Lewis did this work on, okay, based on the DLS table, the resource table, or whatever they call it. Based on this, they find out what is the worth of a player, or what is the contribution of a player to the game outcome, right? So now a game has 22 players, I guess, right? So 22 players. How do you find out who made the most contribution? Quickly, give me some ideas.
This is the run scheme. The most number of runs is played in.
The most number of
Runs.
Okay, so that means a bowler will never have a contribution, a pitcher.
For a batsman.
Now I asked which player is the most, who deserves the most credit for.
So you'll have to factor a lot of things, mathematical index, like runs scored, number of wickets taken, number of catches taken, all sorts of things.
Okay, so there is one thing called the man of the match. It's a very subjective judgment of a bunch of who thinks that this guy did a lot of work, right? I hate cricket, seriously, I hate cricket. And the first thing I talked to this, so Imdad Ullah Khan is the chief selector, so just before going to World Cup, he's asked for a meeting, and the first thing I told him, look, I hate cricket, okay? So I just did the data science part of it, the maths part of it, and I don't like cricket. So, and then, okay, so if it helps us, we'll use it. If it doesn't help us, we'll not use it. So so the man of the match is a very subjective judgment, and it's really a huge bias. The data just tells us towards the winning. It's almost always the winning team gets the man of the match, right? But it gives you some idea of who contributed the most to the wins, right? So you check this thing. We discussed this thing. I gave you an example. If I give you all negative numbers, which is a subset of Z, it doesn't have a minimum, right? So this isn't a well ordered set. Again, this was just so that you know the words, okay? All this whole lecture today was just so that you don't get. Post set is important, comes very often in optimization, and we will see it in graph theory when we do graphs, and you will do it in data structure course and in algorithms course and operating system course and even databases, okay? Joins and what is it called? Join and meets things from posets. Okay, so Hasse diagram is just is a representation of posets, okay? A concise representation, a pictorial representation of posets, right? You have a set S, and on top of it you have a partial order. Some things are comparable, some pairs are not comparable, right? Depending on the comparison direction, you put A is related to B, so you put a a line from A to B, okay? So here is a Hasse diagram of this poset. We have 4 elements in the ground set, and we have less than or equal to relationship, okay? So these lines represent who is related to who, right? Is 1 less than or equal to 1? Is 4 less than or equal to 4? 3 is 5 less than or equal to whatever. 3 less than or equal to 3, 2, 1, right? So that's these loops. These are called self loops. These represent the 1, 1 or 2, 2, 3, 3, 4, 4. Now is 1 less than or equal to 2? So I draw a line between them, okay? Now because of comparability and these things, because I know it's a poset, so there is no point in just writing all the reflexive relationships. Okay, because I know it is anti-symmetric. So if one is related to other, so this is to show that where is the arrowhead going. I just draw all the arrows generally upwards, right? Northwest, northeast, north, right? That's what I do. So I can drop the directions also. So I drop the self loops. I know this is a poset. They must be there. So I don't waste ink on it, right? And just the diagram is very cluttered. and I also draw all the directions are upward. So, I drop the directions, right, and next thing I do is I drop all the what's called shortcuts, all the relations that can be explained through transitivity, I drop them also. So, here 1 is related to 2, 1 is less than or equal to 2 and 2 is less than or equal to 3. Because of this, 1 must be less than or equal to 3, right, but there is no point in drawing this. I can just draw this, because can I reach from 1 to 2? So, anything above, anything for which there is a longer path now are comparable. Okay, here is another example. We have 7 elements and the divisibility relations among them, right, whoever is divisible. Okay. So, these are all divisibilities between these 7 elements, pairs of these 7 elements. What will you do? Drop self loops, drop the self loops, right, and now just drop all the transitivity imposed edges, drop all the shortcuts, right. This is now the comparability, this is the relation. Now, how do we know if something is comparable or not? Okay. Typically, the way we do it, because these two are at the same level. If either 2 was comparable with 3, either 2 was related to 3 or 3 was related to 2, so then 2 should be upward or 3 should be upper than above 2, right. So, because they are at the same level, they are non-comparable, right, and if they are in the same chain, then they are comparable. All pairs in the same chain are comparable. Okay. There is one more word that if you wrote, it's called chain and anti-chain. A chain is this type of this sequence of edges from something, right? It's a path of, and the anti-chain is this the width of this is just like kind of the anti-chain. These two are in one anti-chain. A collection of items, none of which are comparable to each other, is called anti-chain, right? And just with this chain and anti-chain, you can do a whole lot of PhDs in this whole thing. Okay, okay. So that was a partial order. Just again, the purpose was to make you enough familiarity so you don't get scared of it, right? Now we're going to do something really cool, which with a lot of applications in computer science and a lot of beautiful stuff. Sequences in project progression, okay, and all of you should be familiar with this thing. What is a sequence? We know what is a set. We know what is a n tuple. We know what is a what else did we study after sets? Yeah, so we know sets, right? So now it's ordered list of things is called an ordered list of things is called a sequence. It's ordered. We know what is ordered n tuple, right? But this is now a list, not just an n tuple, not a fix. Everything is of one thing, and now we are talking about one fixed thing, not a collection of ordered n tuples or something. Here is a technical definition of this. If you have a multiset S, any function that maps suppose the multiset has n elements, the cardinality is n, right? So any set of any function, any mapping from 1 to n to s is called a sequence, right? An ordered list. So an infinite sequence is a function from n to s, from all natural numbers to s. This is how you should. This is why I think of this as a function, right? So f is actually imposing this order on the sequences, on the elements of the set S. Set is unordered collection of objects, right? A multi-set is an unordered collection of objects where repetition is allowed. So if I want to impose some order, that this is the first, this is the second, this is the third, some kind of arrangement of that, that is called a sequence now. Okay, so this f actually gives an ordering of it that basically gives it basically maps the 5th index to the A5, the 4th index to A4, the 7th index to A7 or so. So that's now an ordering of that. Okay, big words, nothing there. A sequence, this is how we denote the sequence, right? Depending on the application, sometime we'll start sequence from 0, sometime we'll start sequence. The first element will be the 0th element, or sometime it will be the first element. Generally, it will be 1, but if some more computer science related a sequence thing is called a sequence starts with 0. typically. Okay, so we'll either do a mapping from, this is just technical correctness definition, everyone should know, right? Just impose any ordering and you will call, that will call the sequence. Impose any ordering on a set, on a multi-set. Okay, so what is the this AI is called the general term, the ith term, right? What is the general term of this? What is AI equal to? So these are 6 elements are given. A5 is 5, A6 is 6. What will be A is 7? What will be A17? What will be AI? What will be AK? Okay, so this is called the general term. You know these things. Okay, here is another one. What will be the general term? What will be the ith term? 2 times I, right? The ith even number will be the ith term, right? So AI is 2 times I. What will be the general term of this? What will be I? AI. So I plus 2? 2I? 2 into I minus 1. So 2 into 1 minus 1 is 1, that's correct. 2 into 2 is 4 minus 1 is 3, correct. 2 into 6, whatever. 2 into 3 is 6 minus 1. So generally it's with the ith odd number, right? Now when I say the ith odd number, you have to know where the I starts from 0 or 1, right? So if I start I from 0 and this is the sequence, then it should be 2I plus 1. Okay, that thing you have to be careful with this. Here is a thing, another one, 2, 5, 10, 17, 26. What should be the next number? Or let's just do the next number. It's not your ICP. The next, the actual question is different. What will be the next number? Quickly. What will be the next number? 37. Why?
The difference in increasing by 2 is 3, 5, 7, 9, 11.
Okay, that's a good way to look at it, but there is another way. Please remember this, okay? She said the next number should be 37 because this one is obtained by adding 3 to the previous one. This one is obtained by adding 5 to the previous one, adding 7 to the previous one, adding 9 to the previous one. So the next one should be gotten by adding 11 to the previous one. So 11 plus 26 is 37, right? Very closely related answer. The answer I'm looking for is not that. The methodology I'm looking for is not that, even though they are the same. We'll talk about it in a minute, next session. Quickly, what should be the next term? What should be the next term? 37 is correct answer. Can you give me any reason? Can you compare them with squares? What are these in terms of squares? What is 2? Huh? I squared plus 1, right? So that's an excellent. The square and odd summation are very closely related. We'll see that in a minute. Okay. So this is an easier way to write it, is that AI is I squared plus 1. That's a general term. What is this thing? 2, 8, 26, 82, 42. What should be the next term? Quickly. Squares, cubes, power of 2s, power of 3s. Yes, please. Sorry? 3 to the I minus 1. Yes, powers of 3s. This is a sequence of powers of 3s minus 1, right? So this is 3 to the 1 minus 1, 3 to the 2 minus 1, 3 to the third power minus 1, 3 to the fourth power minus 1, 3 to the fifth power minus 1. So next one will be 3 to the sixth power minus 1 and 3 to the seventh power minus 1. So generally speaking, this is 3 to the I minus 1. Okay? Okay. It's a sequence. Now we know it's a general term. We know where, what is the mapping here? What is f of 10? What is f of 10? Describe f of 10, not give me the value. What is f of 10? No, not the value. What does f of 10 means? Sorry? Yes, so it's f of 10 would be like A10, right? So A10, so it's like which position, which number, which element of the set got the ith room, the ith index, right, the 10th index. Okay. Okay, so that's why, because I had to be technically correct there. Let's do the other side exercise. This make sequences from the description, from the journal term. So it's given the terms, sequences are described in English. Now we have to see. So the sequence starting with 10 and each term is obtained by subtracting 3 from the previous term. What is the first term here? 10. Why? Why is the first term 10? Because it says it's the first term is 10, right? What is the second term? 7. And then -1 and whatever, right? Okay. Okay. So the sequence whose nth term is the sum of the first n positive integers. What is the first term? What is the first term? Why 1? So because the sum of the first one positive integer is 1, right? What should be the second term? 3. Why? Because the sum of the first two positive integer 1 plus 2 is 3. What should be the third one? 6. Then 15. What will be after 15? Why?
6. It will be the sum of the first 6.
Yeah. So why is it 21? Yeah, so we will do it. The sum of the first n terms is given here. The ith term is given. First sum of the first I positive integer is given is ai. So I'll just add I plus 1 to ai to get ai plus 1, right? So it will be 21. Okay. So the sequence whose nth term is 3 to the n minus 2 to the n. Quickly, what is a1? Why 1? 3 to the 1 minus 2 to the 1, right? Then what is a2? What is a3? You see, something strange is going on. Why are you getting odd numbers? Okay, these are kind of things we'll study in the next session. Yes, please. Is it wrong? Okay, generally it is wrong, but I can't. I don't know. 3 to the n is product of odd number is odd number. It has to be odd number. It's not important. It's important. It's all odd numbers. We are getting the sequence of odd numbers. 1, 3, 5, 1, 5, 7, 9. Is it correct? It's wrong. 3 to the power 3 is what? 27. 27 minus what? What is it? 19. Okay, so I made a mistake. And what is never? I will never be able to do arithmetic. What is 3 to the 4? So can you please note down so I correct this thing? Okay, but you know how to get this stuff, right? Let's do this. The sequence whose nth term is the largest integer whose binary expansion has n bits. Write your answer in decimals. What's the largest integer you can write in n bits? In 2 bits. What's the largest integer you can write in 2 bits? 3? Why? So why is it 3? Okay. So it's 2 to the I, n bits 2 to the n minus 1, right? So it's a sequence of 2 to the n minus 1s, right? So 2 squared, 2 to the I minus 1, you write it and that's the thing, right? Hopefully this is correct. Okay. So write a couple of more terms if you like, if you want to really understand this thing. And please remind me so I correct the previous question, the answer to the previous question. Okay, luckily it's not ICP. So let's do the sequence whose first terms are 1 and 5. The first two terms are 1 and 5, and each subsequent term is achieved by is obtained by adding the previous two terms. What will be the first term? Second, the third one, fourth, and 17, right? So you can just continue doing this. I asked you to write only 5 terms, so that's why it's only 5 terms. Okay. If a sequence is finite, these are called strings, right? You begin your C++ thing with generally with strings, right? So the first thing is strings. These are just finite sequences. Okay. So then we'll talk about subsequences later, and they're called substring. The length of a sequence or the length of a string, if it's finite, if it's infinite, then length is infinite, right? if it's a string, if it's a finite sequence, then the length is a finite number and we call it length. The empty string, can there be an empty string? Remember the definition, right? So, we go back to the definition of sequence. A sequence is an ordering imposed on a multiset. Now, because set can be empty, sequence can be empty, right? They are strings of length 0, they are sequences of length 0. Okay. Now, you must have heard the word bit strings, right? We saw sets representation as bit vector or bit strings, right? Those are bit strings, are just strings or vectors which coordinates are only zeros and ones. Okay. So, there is a term called alphabet in text analytics and NLP. You will use this thing a lot. Alphabet is basically the set S, is the multi-set S is described as alphabet. It's called sigma if it's a finite string. So, where does each element come from? What types of elements are allowed in the sequence or in the string is called the alphabet. So, if the alphabet is 0, 1, then we call them bit strings. If the alphabets are 0 to 1 digits, then we call them integers, right? If the alphabets are English alphanumeric thing, then we call it English text, right? So, a sequence will be, a book is a string made up of English characters and some alphanumeric, some punctuation symbols and some numeric symbols and something. Okay. So, the set of all possible allowed symbols in a string is called the alphabet. Okay. So, that was just again to give you the words, so you don't worry about that. A geometric progression is a sequence. Okay. So, a geometric progression is a sequence where of this form a times r squared, a times r cubed, a times r to the 4. The next term is obtained by multiplying r with the previous term, okay, or the ith term is obtained by multiplying r to the I with this number with the number a, right. So, the ratio between the next term and the previous term is going to be, okay. So, if you take the ratio of two consecutive terms, right, the term in the denominator is the previous term, this number is called r, this number we get r, and this r is called the common ratio. Why common? Because you take any ith term divided by the ith minus first term, you will get r, right. So, it is called the common ratio, right, and that gives you, if you get a and r, you know the whole sequence, right, the first term or the initial term and the common ratio, how we get the next one. Okay. This is, you guys did it probability, anyone who did probability somewhere, you know geometric random variable, a geometric distribution, no, anyone knows geometric distribution? You didn't do probability. What did you do in probability? You know geometric random variable. Okay. So, not a big deal, you will find out this thing, and geometric random variable is basically this thing. The word geometric there comes from this geometric progression. Okay. In any serious probability course, this should be one of the first random variables you study. Okay. So, a is called the initial term, the next term is obtained by, everyone knows that's a geometric progression, right. In arithmetic progression, you are given an initial term called a, and the next term is obtained by adding d to the previous one, right. So, whenever you take the difference between the next term and the previous term, and this will be a fixed number constant d, right. So, d is called the common difference, it is common between every pair of successive elements, it is the common difference of every successive elements. Take the ith element of the sequence of the progression and the I minus first element, take their difference, you will get d. Okay. So, a is called the initial term, d is called the common difference, the next term is obtained by adding d to the previous term. Okay. Is this a geometric progression or arithmetic progression or neither of them? What is the initial term? Let's see, what's the second term divided by the first term? What's the third term divided by the first term? Okay, what's the common difference? What's the difference? The first, second minus first? What is second minus first? Negative 1 minus negative 1 is negative 2. What's the third minus the second? The third minus the second is 2. What's the fourth minus the third? So they cannot be, there is no common difference, right? The first one is negative 2, the second one is 2, so there is no common, it cannot be arithmetic progression. Let's see what's the second divided by the first terms. What's the third divided by the second? What's the fourth divided by the third? Negative 1. So this seems to be a geometric progression. What's the common ratio? Negative 1, and the general term is negative 1 to the I, right? Negative 1 to the I. Negative numbers raised to the even power is positive and raised to the odd power is negative, right? We know that it's just simple multiplication. Okay, 3, 9, 27, 81, 243. We saw something very close to this. What is this? What is the general term of this sequence? 3 to the n, right? 3 to the I. N is 3 to the n, or a k is 3 to the k. AI is 3 to the I. So is there a common difference? Do you see a difference? Difference is increasing, right? Difference is increasing, right? Yes? What is the, is there a common ratio? What's the second divided by the first number? The third divided by the second, and the fourth divided by the 3. You see a few things, you can kind of see the pattern. The difference is the common ratio is 3, right? What is the common ratio? 3. The general term is powers of 3's, right? What is this thing? 1, a half, a fourth, a quarter, a eighth, a 16th. What is this? Yeah, it's a geometric progression. The common ratio is a half, right? We never said R is going to be positive or negative or bigger than 1 or integer. R is just a number, right? It could be negative. We saw an example of negative. We saw an integer, positive integer. We saw a number less than 1, right? So it's half to the I minus 1 is the term, half to the I minus 1. And now here you see this thing that we have to be careful with, where do we start I from, right? So if I begins with 1, with 0, then it may be half to the I, half raised to the power I, right? And if we begin indexing by 1, then it will be half to the I minus 1. 1, 4, 7, 10, 13, 16. You see common difference here, right? We directly see common difference is 3. So this is arithmetic progression. The first term is 1. The next term, the common difference is 3. The general term will be, so if you reach I steps, how many 3's would have you added to A, right? So A plus I minus 1 times D. So 1 plus 3 into I minus 1 will be the general term, right? The ith term. Okay, 6, 2, negative 2, negative 6, and so on. Do you see a common difference? Common difference of negative 4, right? So it is an arithmetic progression where D equals negative 4 and the first term equals 1 and so on, right? The first term equals 6. Okay? Okay. Do this, is it geometric progression, arithmetic progression? What's the common ratio or the common difference, or neither of them? Some general term, all of these 3 things. So in the previous case, we wrote this type of thing, right? So this is how your answer should be. Okay, so now we are going to do the topic of this section, this lecture is actually summation, right? Sequence is a very simple thing, everybody of you should know this. So now we're just doing some vocabulary for our language, and then we'll do some methods. Okay, the next session will be just some method. Here is what you see, this big ugly thing called, no, not ugly, it's very beautiful thing, sigma. This converts a sequence into a series or a summation, right? It's a big method, it's a big operation performed on a sequence. It gives you one number, right? So you can think of it as a function, either C++ function or a mathematical function. which takes a sequence and outputs a number. Okay. So, for this sequence is this is simple vocabulary. Whenever we see this thing, this is pronounced as the summation of ai, summation of whatever is written here, whatever these are called summands, whatever is being summed, the summation of ai's when I goes from 0 to n, right, when I starts from some index of the sequence and ends at some other index at the sequence, right. If it is an infinite sequence or finite sequence, depending, we have to be careful with the upper limits and the lower limits. So, it just outputs the sum of all these numbers. Okay. A0 plus A1 plus A2 plus AN, all of these numbers are added together and it is returned here by this from the summation. Okay. Here is what, if I want to add all of this array, or this could be a longer array, but I am adding the first 18 terms of it, right. So, I can write the sum from I equals 0 to 17, the value ai is written in the array, the first element in the second element in the 18th element, and so this will be, this basically adds up all these numbers here, right. So, sequence of numbers, it works on sequence of numbers, not on sequence of characters, not on sequence of people, not on sequence of other thing, right. So, the addition operation has to be defined. We do not have to have 0 and n all the time, all the summation, it could be anything. So, sum when I goes from the sum of ai when I goes from L to M, L is the called the lower limit, M is called the upper limit. So, if I want to do something like this, I want to add the first how many elements are there? 8 elements. If I want to, no, it starts from 0. So, this is how many elements? 9 elements. If I want to add the first 9 elements, I will write like this, sum I goes from 2 to 10, sum of ai, right. So, it will give me from this array, it will give me the sum of these elements. Okay, clear? Language is clear? Summation is clear? This, so let us see, I have this thing. How would I write this in summation? So, we know from sum to come up with the basic arithmetic method, just like the the binary operation in the usual arithmetic we do. How would you write this? Yes.
So, it's summing from 0 to n and put a significant I.
Sum of I, right, because if you look at this as sequence, forget about this, replace this plus sign with a comma, then it is a sequence, right. What is the general term? Let us say we begin with 0, the general term A0 is 0, AI, A1 is 1, A4 is 4, right. So, AI is I. So, I am adding AI which is equal to I, so I am adding I from when I goes from 0 to n, right. So, I equals 0 to n I. This is how everybody can see this code. Can everyone see this code, right? This code is going to compute, it's just an iterative sum, it's just a repeated sum, addition being repeated multiple time, right. So, I goes from 0 to n, this is how for loops are pronounced, when for I equals 0 to n, increment with plus 1, and you can write sum equals sum plus I, right, or sum plus equals I. Is this clear? All these four things are just describing the same number, right, one number described in 3 different ways, right. You can write in many other different ways also. Okay. How would you describe this? The first n terms of 0 plus 3 plus 8 plus 15 plus 24. What is 3 plus 8 plus 24? That was the squares minus 1, right. 4 minus 1 is 3, 9 minus 1 is 3 squared minus 1 is 8, 4 squared minus 1 is 15, 5 squared minus 1 is 31, 25, 24 and so on. Yes. So, if you add them, you will get, this is how we will shorthand notation for it. Some I goes from 1 to n, I squared minus 1. This is the C++ way of saying the same thing, right. It is a different language, it says the same thing in different ways. Now, we now onward talk about our language and then we come back to this in a minute. Everybody agree with this? I am going to give you some applications of these things and let us do some exercises. write this, how many terms are there in this summation? This is a summation symbol, right? The sum, can you pronounce this? Pronounce this, what is this written here?
The sum of 2i square when I is equal to 3.
When I goes from 3 to 6, right? Okay, sometime we will have to say explicitly I goes from 3 to 6 inclusive, or right, I is within the range 3 to 6 inclusive, right? So, okay, so what is this? Give me the answer to this right now in expanded form. What is the expanded form of this? No, not the values, just don't worry about the values. 2 into 3 squared plus 2 into 4 squared plus 2 into 5 squared plus 2 into 6 squared plus 2 into 7 squared, right? Why will the 2 into 7 squared there? Why would 2 into 7 squared be there? It won't be there, right? 2 into 7 would be there. The range of I, or the loop, the iteration, the loop begins at I equals 6, 3 and ends at I equals 6. The moment I hit 7, it will be, loop will terminate, right? Clear? Write this thing, I equals 4 to n, I equals 4 to 1, n equals 4 to n 1 n cubed. This n and I, these are just running variables, right? These are called loop counters. The sum of n cubed, give me this thing in different, in expanded form. 4 cubed plus 3 cubed plus 2 cubed plus 1 cubed, right? Okay. Do this, don't jump to solutions. I equals 1 to 3, the sum of I squared plus 2i plus 1. What is I squared plus 2i plus 1? This I plus 1 whole squared, right? Now it's much easier. Can you tell me a few terms here? What is the first term in this summation? 2 squared, then 3 squared, then 4 squared, then that's it. 3 terms here, 2 squared plus 3 squared plus 4 squared. Okay. Okay. 2j equals 6 to 3j squared. Give me some terms here quickly. What's the first term? So look at this 2 multiplied by something. That something is a number, right? The summation is a number. So this 2 is common multiplied with all of them. So what will this be? 2 into plus 4 squared plus 3 squared, right? So each one will be multiplied with 2. Yes? Do you notice something? The first one and the last one are the same. Why is that? Yes, and what else? There is still differences there, no? Why can we do that? Why is the first one equal to the last one in answer? Addition is commutative or associative, not distributive. Distribution requires 2 things. One distributes over the other. It's associative, or which follows from commutativity of this. Okay? Don't do the numbers. Why? Why is the number important? Pay attention to the method or the concepts, okay? Not the answers. Answers are all okay. Okay, so now let's just see why are the first and the second equal, or is it just a coincidence or something, right? Then let's just do some what's called change of variable. The most beautiful trick you can do, the first is change of variables, application of linearity of summation. Are those of you who have done probability ever heard of linearity of expectation? Ever heard the word linearity of expectation? Linearity of expectation? No? You know expectation? Okay, so there we say expectation is linear. Why? Because summation is linear, right? Expectation is just a summation, just average, right? So it's an average thing, weighted average, and average is just the sum divided by the amount, right? The volume, the sum divided by the number of items, the number of items in the summation. So expectation is also the average, and okay. Okay, so the change of variable, look at this thing, everyone, we can see this thing, right? This is j plus 3 when j goes from 1 to 6, right? We have to add j plus 3 cubed. How many terms should be there in this summation? If I am going to expand it, how many terms should be there? 6 terms, right? The terms are not necessarily j cubed or whatever. So this is when j is 1, it's 1 plus 3 cubed, when j is 2, it's 2 plus 3 cubed, and so on, right? It's easier, so now we can do many ways. Remember, we did here one, I squared plus 2i plus 1, we translated into I plus 1 whole square, right? We essentially changed the summation term equivalently. We can't just replace it with anything differently. We can't just replace it with other stuff. It has to be equal, but sometimes it's more convenient to think of stuff in one way or sometimes it's other. So j plus 3 cubed, what if I do, if I substitute instead of j plus 3 I write k, right? So I just substitute k for j plus 3. What will happen to the summands? The summand will become, we just said j plus 3 is now k, right? So will be k cubed, right? But what will happen to indices? That has to be done carefully. When j is 1, what is the value of k? When j is 1, what's the value of k? Okay, so k should begin at 4, and when j is 6, what's the value of k? 9. So these two terms, this summation is exactly equal to this summation, right? Occasionally, right, in the next session when we see this thing, this will be just a number. We will all know this stuff, what's called the closed form of this thing, right? What will be the output of this loop? We will know this thing. Now, it may not be, we may not directly be able to say that j plus 3 cubed, the sum of j plus 3 cubed from some index to some other index is something, right? So it always, it's very, very helpful to see, to look at summation, to use the change of variable tricks, right? So I was going to tell you there are 3 important tricks for summations, right? One is the change of variables, right, which is exactly the same as the next trick. The next thing is called linearity of summation, and the one afterward, which is roughly the same as, if you really think about it, it's the same as change of variable, is the order of summation. Occasionally you order the summation differently, right, and it becomes adding. So this example, we saw this here. Here we are adding from 6 squared to 3 squared, doubles of 6 squared to 3 squared, and we are adding here the doubles of 3 squared to 6 squared, right? It's the same thing, addition is associative. So this changing the order helps, right, a lot, and especially when we have multiple summation, nested loops or nested summation, and it also even in single summation, sometimes it makes life extremely easy. Okay, at least you're not scared of the big terms there. Okay, so hopefully you would remember some linear functions. A function is linear. This is not our function. This is numeric functions. Our functions too. This function is called linear function if it has this property that the output of the function, if I take a linear combination of the inputs, right, if I take a linear combination of 2 inputs, and the output of the function will be actually the linear combination of the 2 outputs. Okay, that's why linear and linear combination, for those of you who know some algebra matrices, you should know this thing, and linear combination is just a the scaled sum of vectors, right, or points. So if I take 2 inputs x and y and multiply each with some real numbers a and b, so f of ax plus by can be computed by just taking the a times the output of f on x plus b times the output of f on y. Okay, if this property is true, the function is called linear. Right? The best way to understand this, suppose my function g works like this, right? So suppose g is defined as like, so g of x is equal to x squared, right? Now let's say if instead of a number, I give it a linear combination of 2 numbers, right? What does it do? What does it do? So G of shall I take a fixed example, or let's just, what is G of Ax plus By? Quickly, Ax plus By whole squared, right? Whatever input it takes, it gives you the square of that input. So it will be the square of Ax plus By, right? Which is equal to a squared x squared plus b squared x squared y squared plus 2abxy. Yes, that's just product of two polynomials, right? Okay. So what is a times g of x plus b times g of y? What is g of x? Ax squared. What is g of y? Y squared, right? So you see, a times g of x plus b times g of y is not equal to a times the g of ax plus by, right? Significantly different. That one is multiplied with a, this one is multiplied with a squared, and then there is this cross product term, right? 2abxy. Okay. Why is this not true for this? Because g is not a linear function, it's a quadratic function, right? So a function is linear if this property is there. And you take any linear function like 10x or x divided by 17 or 14.3x, negative 14.3x. If g is that type of thing, you will see this thing take a linear combination, it will come out. Okay, the function is called linear if it maps a line to a line. A linear combination is a line. Okay, so so this we know summation is linear. By this we mean the sum of ax, the sum of p times ai, some sequence ai and some sequence bi, the sum of p times ai plus b q times bi is equal to p times the sum of ai and q times the sum of bi. Okay, this is what we say summation is linear. Okay, not very hard to prove, it's just linguistic things, we just defined it. I'm going to give you a proof of this, just intuition of this. It's no proof as such, it's just a very simple statement. These are these self-evident truths. We know this thing. General form, let's say q is 0 or there is no such sequence as p, or if q is 0, then it says the sum of p times ai is equal to p times the sum of ai, right, for the same indices and everything. Why is this true? Well, this is, everybody agrees with this. We saw these examples. 7 times I squared is basically from I equals 1 to 3. I couldn't write too many terms, so let's say I equals 1 to 3 is 7 times 1 squared plus 7 times 2 squared plus 7 times 3 squared, right? And from this we can take a 7 common out. We remember that common out, you can do this common stuff because addition is linear, summation is linear. 7 times I squared is actually 7 times 1 squared plus 2 squared plus 3 squared, and that is actually, if you look at 1 squared plus 2 squared plus 3 squared, earlier we saw this kind of translation from sequences to summation, the general term and general term to specific terms. 7 times I squared. Does everybody agree with this line? With all these equalities here, right? This very simple common sense. So this is an example of linearity of summation being applied here, right? Generally speaking, sum of p times ai when I goes from 1 to n is going to be p times a1 plus p times a2 plus p times a3 all the way up to p times an, right? You take the n terms of ai and of the sequence ai and multiply each with 7 and you get this thing, right? Now what is 7 times a1? It's just times a1. 7 times a1 multiplication is defined to be is this thing that a1 added 7 times, the p times, right? P times a1 is just a1 added p times, right? So this 7 p times a1 is a1 plus a1 plus a1 up to p times. P times a2 is a1 a2 plus a2 plus a2 p times. P times ai an is equal to p a1 an plus an plus an, right? Okay. Now addition is associative. I can just take the first term of among the first p, the first term of the second p, and the first term of each term, and I can just rearrange them. I can do it in any order, right? The addition I can do in any order. So if I do that, take the first a1 here, first a2 here, the first a3 here, and the first an here. That's one group. Then the next group is the second a1, the second a2, the second a3, and the second an. Then the third one, right? I will have n groups, p groups, right? Each group is summation ai, right? A1 plus a2 plus a3 up to an is summation of ai when I goes from 1 to n, right? And this will be repeated p times, and that's equal to p times summation ai. Is this clear? This is when the law, when you were told that, oh, you can take p common out, you can take p common, right? That's the p common thing, is basically what actually was the linearity of summation. Okay, can you take p common out for multiplication? If you have p times x multiplied by p times y, if you have px times py, can you do this?
That's pxy, short.
Yes, can you do this? You can't do this, right? These are not equal. Why? Because multiplication is not linear, right? Addition is linear. If you have this thing, then you can. This is equal then. Okay? Okay. So, okay. Let's see why would you need summation. So, I am going to go to multiple summation in a minute, but why would you need summation? Remember this thing from day one? Gauss was told to add the first 1000 integers. He did it in 30 seconds. How? Because you would be able to, when we study summation, we'll do this. There's many applications. You don't have enough vocabulary for that. When you do algorithm analysis, you're going to love this thing. Okay, you're going to use a lot of these techniques. Okay. So here is a sorting algorithm. We talked about this earlier. It's called selection sort, right? Every time you find a minimum and write it in the first place, then find the minimum of the remaining, write it in the second place, then the minimum of the remaining, write it in the third place, and that gives you a sorted array. The question we ask is how many comparisons are performed, how many times the blue statement is executed, right? So let's just do it now. The blue statement, how many, there is no blue statement here, or is it blue? It's not blue. Okay. A1, how many J's A1 is compared with? How many AJ's A1 is compared with? When I is 1, A1 is compared with for each J, where J goes from I plus 1 to N, right? So who is AN compared with, A1 compared with? It's compared with A2, A3, A4, A5, and so on, right? So this is, who is A2 compared with? A3, A4, A5, and so on, right? Is it clear? AN minus 1 is compared with AN only, right? When I is n minus 1, j goes from n plus n to n, which means only 1. So an is compared with nothing, right? J is already bigger than n plus n, so then that's why the j will not go. There will be no iteration for that, right? So the number of comparison here is, how many comparisons are here? How many comparisons A1 undertakes? N minus 1. How many comparison A2 undertakes? N minus 2. So the total number of comparison is actually the summation. You see, it's an algorithm analysis question, the algorithm difficulty or runtime question, and that is answered by a summation, right? So the ability to do these summations, these are toy examples, but you will see when you do algorithm that these are just actually all the summation tricks are used a lot there. Okay. Here is another counting question which is exactly the same. Remember, we had n teams, each team play every other team, right? It's a graph theoretic question, we will see this later. Each team play every other team. We want to count the number of games, right? So we can count it this way. Team 1 plays with all of these teams, right? So from team 2, team 3, team 4, or team up to team n. Team n plays, how many games does team 1 plays? N minus 1. How many games team 2 plays? right? So team 2 plays with team 1 and then team 3 and team 4, right? So this every team plays exactly n minus 1 games. Okay. So what is the total number of games being played? What is the total number of games played? N into n minus 1. Okay, actually slightly less than that, because look at this game between team 1 and team 2, and the same game is written here, team 2 to team 1, so it's counted twice. So I have to take care of that, right? So the total number of games is not n minus 1 into n, it is n minus 1 plus n minus 2 plus n minus 3 plus n minus 4, okay, which is, so total number of games is now the sum of this column, right? Sum of this column is what we are learning how to do it. Okay, seen this picture? Everyone should know integration, right? The integration is just, so they wanted to do summation, but they wanted to earn a little bit more money, so tried to sound more important or doing something important, nothing, okay, it's just summation. Integration is just summation. Remember area under the curve? What do? We just divide it into small rectangles, and then because rectangle area finding is quite easy, we just add the areas out, right? And that gives us the integral of the thing. Okay, so what they okay, so we'll talk at some other time what is actually derivative, right? Why do they so that's actually telescoping some in a minute, we'll talk about some other time about that. Sometime occasionally, this is just one slide, occasionally we use the product symbol. Again, I just want to show you so you don't get scared if somebody use these big words in front of you, right? If you have a sequence and you want to take the product of all those terms, you can write it, a shorthand notation for that is the product of ai when I goes from 1 to n or something. Okay, so the product of ai when I goes from n to n is written as this big product symbol. In LaTeX you write slash capital P R O D prod, right, and that will give you this. If you want to have, if you have a 2D sequence and you want to add them, if you have a 2D sequence, a matrix or something like that, right? So two-dimensional sequences, or so suppose I want you to add all the numbers. Previously for matrices, for sequence, I told you add all the elements in a sequence, add all elements in the array. Now the sequence is 2D, it's indexed by two variables, the ith variable, the jth variable, the column and the row, right? The numbers are arranged in a 2D place. So I want you to add every element in this sequence and this matrix, and that can be done by just writing what's called a double summation, right? The sum when I goes from 1 to n1, some number n1, and when j goes from some number from 1 to some number n2, add aij. Make sense? So add every element in this matrix. It's shorthand, big summation, a11 plus a22 plus a33. You can just write them in a very concise way like this. Okay, it adds up this matrix. This is how we write nested. This is called double summation or nested summation. The jth summation, the summation indexed by j is nested into the summation indexed into I. That's nested loop. If you are going to take the sum of this matrix is a 2D array in C++. This is the code for I will 1 to n1 and j goes from 1 to n2. You add up aij, right? This will be exactly this matrix and it will be added this thing. Okay, again just vocabulary, okay, just words. Ever heard of row major and column major summation? That basically is saying the sum of aij when I goes from 1 to n1 and j goes from 1 to n2 is the same as the sum of aij when j goes from 1 to n2 and I goes from 1 to n1, right? One of the most important thing in summation, this is just linearity of summation. When you see a double summation, you can flip the order, right? That's because you're just looking at a sequence of vertices, either row major or column major. That's your choice, right? You can do that. It's going to be exactly.
How might this help us? Why will this
Oh, it helps us a lot. We'll do examples and we'll do this thing. It helps us a lot. Okay. The first thing you should do every time you see a summation, chief looking at it the other way around helps. Okay. No lower triangular matrix, upper triangular matrices, right? If I want to give you a 2D sequence, but I want you to add only the lower triangle part of it, right? A 2D matrix, a matrix, and I want you to add the lower triangle part of it. This goes, I goes from 1 to n1 and j goes from I to n2. J starts doesn't start from 1, j starts from, okay, so I think I made a mistake here. This is about upper triangular matrix. It should be j starts from 1 to I. Okay, j starts from 1 to I will give you this picture, right? Take the the lower triangular matrix, including the diagonal. If j starts from I plus 1, then it will be excluding the diagonal. Upper triangular matrix, but excluding the diagonal, the equal element. Okay. Okay, this is the code for if you want to add up, sum up all the elements in the lower triangular matrix. Again, this is upper triangle matrix code. So I'll change the diagram now. You can add any subsequence or any subarray, just like for subsequence, you can have a different lower order, lower limit and upper limit. So this you can do also here, right? If you want to add only those sequences that are in row L1 to Li to Ni and Ui and Lj to Uj, you can write this code, and this is good. Okay, good. So tomorrow we'll do techniques of how to find the values of summation.